Alright, so I'd like to pick up where we left off last time. We talked about the conversion between radians and degrees, or degrees to radians. Through the applet that I showed you, which is still on Schoology under section 5.1, if you want to look at that. Quick video of basically showing you how a radian is defined. We find out that either 2 pi radians is equal to 360 degrees, or we can divide both sides by 2 and get pi radians is equal to 180 degrees. Okay, so that's a conversion factor that we are going to use to flip-flop back and forth between radians or degrees. Kind of talked about the comfort level that we have is probably with degrees, but radians are better within a lot of our calculations. They're just a little bit more natural than working with degrees. So what we're going to do is just like any other conversion. If I asked you to go from, let's say, there you go. Let's say I go like 1.2 kilometers, but I want you to convert that into, maybe how many feet that is. We're going to use unit analysis, and what we would basically do is say, okay, well, I don't know anything about a conversion factor from kilometers to feet directly, but I do know how to get kilometers maybe into meters. And basically what I do, I want kilometers to be on the bottom because there's one on the top already, so that they cancel. And then if I do my calculations here, my units right now would be meters. So again, I don't know how to get meters to feet, but I do know how to get meters into centimeters. So we do that to where now our meters would cancel, and our centimeters would be the only thing left over. Now, likewise, I still don't know how to go from centimeters to feet, but I do know how to go from centimeters to inches. Okay, and I've been ignoring the values here. We have a conversion factor that says there's 2.54 centimeters for every 1 inch. And now centimeters would cancel, I'd be left with inches. Well, I do know how to get inches into feet now. Inches would cancel, and then if I have the correct values here, I should be able to be left with feet. So meters to kilometers, so there's 1,000 meters for every 1 kilometer. Centimeters to meters, there's 100 centimeters for every 1 meter. We have this factor here, and we know that for every 1 foot, there's 12 inches. So if I multiply that out, I should be able to get how many feet there are in 1.2 kilometers. Well, the same thing, the same procedure, so that's unit analysis. The same thing happens when we talk about radians and degrees. Now, here we used, 1, 2, 3, 4 conversion factors. Obviously, we're not going to have that many when we go from radians to degrees or degrees to radians, just the one. But the same argument applies, okay? So you can remember these 2 little rules right here if you want. I don't know them off the top of my head. I just know that the conversion factor is pi over 180, or 180 degrees equals pi radians, and then using that along with the understanding of how dimensional analysis works, I should be able to convert anything from one unit to the other. So here's some examples. Express 60 degrees in radians. So basically what we're going to do is we're going to start with 60 degrees, and we want to get an answer in radians. So right now this is 60 degrees, like over 1 if you want to write it that way. So now I need to multiply that by my conversion factor. Well, I need degrees to cancel, so degrees need to be down here. And if degrees are down there, and I need to be left with radians, then radian needs to be up top. And in the comparison, so I know where degrees, I know where radians have to be, so the 180 is always the degrees, and pi is always the radians. So if we multiply this out, we get 60 pi over 180. Okay, 60 divided by 180 is 1/3, so we get 1/3 pi radians. So 60 degrees is the same thing as pi over 3 radians. That's actually going to be a pretty useful and very common conversion that we use. And eventually you're not even going to do this. You're going to know 60 degrees just links to pi over 3. Kind of like how you know 1/2 links to 2/4 or 2/4 links to 1/2. You're going to be able to make those conversions. Or that 12 feet is, or sorry, 12 inches is 1 foot. You know that conversion by heart because you've used it so many times. The same thing's going to happen here. Couple others here if you want to go 90 degrees and change that into radians. Then, okay, degrees is up top, so degrees has got to be in the bottom here. So that means radians has got to be there. And we have pi over 180. So we multiply that together, gives me 90 pi over 180. The degrees have canceled, so that's why I don't have those units anymore. And now 90 divided by 180 is 1/2. So I got 1/2 times pi, what we call pi over 2 radians. So 90 degrees is equivalent to pi over 2 radians. Okay. You can keep doing, but the proportionality is constant. So we see that 180 degrees equals pi radians. So if I cut 180 in half, that would have given me this 90 here. So then cut that in half, and it gives me the pi over 2. So if I take 90 degrees now, and we know that that's the same as pi over 2 radians, cut 90 degrees in half, you get 45 degrees. Cut that in half, or multiply by 1/2, you're going to get pi over 4 radians. So there's some proportionality relationships there that exist that you can do that with. If I'm going the other route, I've got pi over 6 radians. Okay, and I want to get this into degrees. So degrees need my symbol left over, my label left over. So down here in the bottom, I need radians so that they cancel, and degrees should be up top. So I have 180 degrees and pi right there. So what's going to happen here, you see that the pi's cancel, left with 180 times 1 on top. On the bottom, you're left with 6. 180 divided by 6 is 30 degrees. So pi over 6 radians, same thing as 30 degrees. Next one, let's do 2 pi over 3 radians. Okay. Now just think about this. We already did pi over 3 radians with 60 degrees. Well, if I double this to get 2 pi over 3, then double that, I should get 120. So let's see if this conversion factor gets me 120. So radians up top, so radians got to be on the bottom. Degrees up top, I'll be left with degrees in my answer. So 180 degrees for pi radians. So pi's are going to cancel. 2 times 180 is 360. 3 times 1 essentially is 3. 360 divided by 3, 120 degrees. And that's kind of what we anticipated happening from that relationship. So no matter what they ask you, if I go, let's say 20 pi over 7, and that's in radians, and I want to change that to degrees. Well, I'm going to multiply by radians on the bottom, degrees on top, so 180, and then pi here. So the pi is going to cancel, and I get 2 times 18 is 36. I'll have 2 zeros there, and we'll divide that by 7, and that will be whatever that equates to as a decimal, would be how many degrees 20 pi over 7 radians is. So when we talk about angles, we're going to talk about something called standard position. We kind of talked about this a little bit last session, where with every angle, the positive x-axis is our initial ray. Our vertex is going to be located at 0, 0. and then our terminating ray is going to terminate or stop in either the first, second, third, or fourth quadrant. Okay, that's called standard position. This angle can be put anywhere. Okay, so this angle here, we could see if I can grab it and move it there. It's the same angle right there as it is down here, but it's a lot more difficult to work with this angle up here, maybe not knowing what the coordinates are of the vertex. Even if I did know the coordinates of the vertex, it's still going to be difficult to find that angle measurement. But if I can move that back down to be based at the origin, with the vertex at the origin, and the initial ray being the positive x-axis, it's going to make our work a lot easier to find that angle and to use that angle in some calculations. So that's what we refer to as standard position. This is going to be a positive angle. Okay, this one here we would refer to as a negative angle because of the rotation, the direction of the rotation. Okay, and this arrow here is showing us that direction. This one over here is just basically showing that if this is your initial ray, then that initial ray has traveled one complete rotation all the way around to 360 and then gone a little bit more. So this angle here is greater than 360 degrees. Okay, but it's going to be less because this would be 360 and then add another 90 to that, this would be 450. Okay, so this angle here that they're showing in red is going to be between 360 degrees and 450 degrees. What we're going to find out is that our angles can and often do exceed 360 degrees. And I know that's a pretty big jump where from 2 days ago, 3 days ago, just having our geometry knowledge, we thought angles or new angles to only be as big as 180. First day trig, we say, well, they can be bigger. They can be up to 360. Now I'm telling you that there is no end to them. They can be as large as we want them to be. Okay, we can have angles that are, millions of decimal places long. Okay, but that being said, let's take a look here at a concept that's pretty useful. So I've got that point there, and I've got this ray. I'm gonna call it, that's gonna be my initial ray. I'm just gonna keep it black, but make it a little bit thicker. And then let's take this one here and make it red, and that'll be my terminating ray. Okay, so right now I'm going to ask it to just tell us what the angle is between those. I went in the wrong direction. Alright, so that angle is 35.28 degrees. Alright, so what we were demonstrating there is that we have a positive angle here. We can rotate, we can come all the way around, so we've rotated and get back to here, and that's 360 degrees. Now, just the way GeoGebra is programmed, it's not going to continue the counting, but that 360, and then if I keep going, so let's say that I get to about right there. So 360 plus this 30.47. So that angle that I just traced out, which what GeoGebra doesn't do, but your text will, like a static picture will do, is it will show you that we have, and this is the way it does it, is that they'll show one complete revolution like that, and then they'll go a little bit further to show you where it stops. So that there is showing you that we went to 360 degrees, but then we're going to go that a little extra 30.47, so we would have an angle here, this angle kind of in this, I don't know, magenta color here, would be 390.47. Okay, 390.47, and that's fine. You can have angles, like I said, bigger than 360. However, that sometimes becomes a problem. We're going to address that here in a little bit, how we can make our work a little bit easier if we do indeed have an angle that's bigger than 360. This one here, we go around, come here, we get, there's 360 degrees from following that to there, and then go another 90, so there's 450. Go another 90, so that's 540. So this angle here that they're tracing out is bigger than 540, but it's going to be, what, less than 630. Okay, so somewhere between 540, let's call it X for the angle, and 630. Obviously, again, an angle bigger than 360. Okay. What we find out though is that we can make our lives a little bit easier. If I do get this angle that's between 540 and 360 or 630, or this angle that is between 360 and 450, I don't want to deal with something that big. Okay, so we get what we call coterminal. Co meaning together, terminal meaning terminating or ending. So these are going to be angles that end together or end in the same spot. Okay, so it says two angles that have their sides coincide. All right, both of them are going to have the same initial ray. Both of them have the same terminating ray. Okay, examples A and C here are that exactly. Okay, so if I look at these two together, okay, this blue ray and that blue ray, the terminating rays are identical positions. The initial ray here is the exact same thing as that initial ray there. Okay, so what I'm arguing here is that this angle here, let's say that angle right there, which would be this one here, let's say that is, I'll just say 40 degrees. Then this angle here is still 40 degrees, but we first realized that we went around one complete revolution, so we went around 360 degrees first, followed up by another 40, so 400 degrees. So a 40 degree angle and a 400 degree angle, they are to be what we call coterminal, meaning that they terminate the same spot. So what's that mean? It means that this 400 degree angle, everything that we want to know about it can be learned through this 40 degree angle. Everything that we want to learn about this 400 degree angle can be learned or known from this 40 degree angle. Okay, so it says find angles that are coterminal with an angle of 30 in standard position. If I give you, let's go to the GeoGebra here. I think I can set this up quickly enough to get a 30 degree angle. So I want an angle with a given size, select leg point, vertex. Okay, so, and we'll just say, we'll go with alpha, and let me put alpha in there. Maybe we can go lowercase a. Let's make this thing go by, let's go from negative 720 up to positive 720, and let's go by increments of 10 degrees. Alright, so if I can get this thing demonstrated here. Okay, so right now we'd be looking at, where'd that ray tool go? Vector tool, there we go. Alright. So this slider is just basically going to control the angle here. So if I go 10 degrees, okay, we'd have that angle right there. But now if I go around a total of 360 degrees, we get back to there, and you see that's still the same 10 degrees, but this is showing that it was actually 370 degrees that we realized. So 370 degrees and 370 degrees and 10 degrees are coterminal angles. Okay, if I wanted to go, 30 degrees, you see 30 degrees, and 390 degrees are coterminal. 40 and 400, 410 and 50. So we can see we've got coterminal angles there. If we would have gone the opposite direction, so let's say that we want to talk about a negative 20-degree angle. Okay. There are some applications, and some people just prefer. I don't like talking maybe about a negative angle. There's going to be a lot of relationships that allow us to kind of eliminate that possibility of dealing with a negative angle. And one of those relationships is to say, okay, well, if I don't like a negative 20 degrees, let's just take, if this is negative 20 degrees and this red ray is the terminating ray, let's rotate it 360 degrees counterclockwise and get it back to itself. If I start at negative 20 and I rotate it this way 360 degrees, it now gets down to an angle of 340. So 340 and negative 20 are coterminal angles. So what we find out here is that the way that we're going to determine coterminal angles is we're going to take the angle provided. So I'm just going to write alpha, okay, is equal to theta plus or minus 360 degrees, okay, or alpha is equal to theta plus or minus 2 pi radians. Okay, so just some notation here. So theta, that Greek letter, is going to be the angle right now that they're giving us. Okay, alpha is going to be the angle that is coterminal with theta. Okay, so that's just how I'm going to identify these things. So if I'm in, I pay attention if I'm in degrees or if I'm in radians. So here they say theta is 30 degrees. So to find an angle that is coterminal with that, I'm going to start adding 360. And then actually we could do it this way. Let's throw on a K here and a K there and say for both of these, K is an integer. K is an integer. Now, because I say K is an integer, that can actually allow me to get rid of the plus or minus. I can just say plus, because if then Z was like negative 1, it would turn into minus 360. If it was negative 2, it would turn into minus 720. Either one. I'm just saying this is kind of redundant to have the plus or minus here. But basically what I'm going to do now is if I'm in 30 degrees, I'm going to add multiples of 360. So I can add 360 once, and that will give me 390 degrees. So that's a coterminal angle with 30. If I want to add 360 twice, okay, so it's going to be 720 plus 30 is 750. Okay, and you can keep doing that. You can keep adding 360 as many times as you want, and you'll keep getting coterminal angles with that 30. Okay, so in this case, this 1 would have been the K equaling 1. This 2 would be K equaling 2. We can do 3. And keep going as far as we want. Well, those are positive coterminal angles. Maybe I want negative coterminal angles. So if I want negative coterminal angles, we can do it a couple different ways. We can keep the K's as positive numbers 1 and 2, or we can just say we'll go 360. Do 30 first. 30 plus 360 times K, but let's let K be negative 1. So if K is negative 1, it's going to be 30 minus 360, essentially, if I evaluate that. And that's going to give me then 30 minus 360 is negative 330. So negative 330 degrees is a coterminal angle with 30 degrees. And kind of think about that, negative 330 degrees. So 30 degrees would be something like that in the first quadrant, 30 degrees. Negative 330, okay, so there would be negative 180. There would be negative 270 if I stop there. Just adding up multiples, so this would have been 90 degrees, 90 degrees, 90 degrees. And then if I go 60 more degrees, so this was negative 270, 60 more degrees would be negative 330. And what would be left over to get down to essentially 360 again, I'd have to follow this 30-degree angle there. So I will see that negative 330 is the same thing as positive 30. We could do 30 plus 360 times negative 2, which again, that turns into essentially 30 minus 720, and that will give me negative 600, go on, negative 690 degrees. So that's one way of doing coterminal angles, and that's again using degrees. So the next one says, well, let's do it in radians. Well, 360 degrees is equal to 2 pi radians. So it's the same exact approach. I'm going to add multiples of 360, but in this case I'm in radians, so I'm going to add multiples of 2 pi. So if I start with pi over 3 as my theta, I was kind of doing it kind of weird up here. I don't know if I followed up here the same kind of notation that I did. I guess I should have used alpha. It doesn't really matter, the notation of this instance. But if I'm going to take pi over 3 and find coterminal angles with it, then I'm going to add to it 2 pi. Okay, and I add to it once, and then maybe I'll take 2 pi over 3 and add 2 pi to it twice. And I can keep doing that as many times as I want. Now, the only thing here with this is because traditionally and just generally, your radians are going to be fractions. So what we like to do, instead of adding it as 2 pi, I'm going to add, so I'm going to go pi over 3 plus now 2 pi with a denominator of 3 would actually be 6 pi over 3. That's still 2 pi. And that just allows me to do the addition of the numerators a little bit easier. I get 7 pi over 3. So 7 pi over 3 is coterminal with pi over 3. And now once I have this as 6 pi over 3, it's really easy to change k to be 2, because now if I just multiply, so I had pi over 3 plus, now 2 pi is 6 pi over 3, but k is 2, so the 6 pi over 3 turns into 12 pi over 3. So I got 1 pi over 3 plus 12 pi over 3, and it gives me 13 pi over 3. And what you can see here is that, 7 pi over 3, add to it 2 pi, you get 13 pi over 3. Okay, and we can keep doing that in terms of adding and getting positive coterminal angles. If you want to subtract, so we go pi over 3 minus 6 pi over 3, and that will give you negative 5 pi over 3. So that's a negative angle that is coterminal with pi over 3. And that's usually what your homework is going to ask you to do. You say, here is an angle in either radians or degrees. Find one positive coterminal angle and find one negative. Okay. Here it says, in this example, it says this is kind of similar to that. It says find an angle with a measure between 0 and 360 degrees that's coterminal with the angle of measure 1290 in standard position. I think the easiest way to do this is just basically, we now know what our angle is that we're looking at, 1290. This is really easy to do. We take 1290 and we're going to subtract 360 from it. Okay, so it gives me 930. I'm going to subtract 360 again, and it gives me 570. I'm going to subtract 360 again, it gives me 210. I'm going to stop when that number, that difference that I get, is between 0 and 360. So 210 degrees is coterminal with 1290 degrees. And the reason we want to be able to do this, I'm going to give you a little snapshot of what's going to happen in the future. They're going to ask you, can you find the cosine? Just going to make sure I'm in the right mode here. We're in I want to go to degrees. And the way I choose that, and we'll talk about this a lot during the class, is the problem was in degrees, so my mode needs to be in degrees. But they might ask you, what is the sine of 1290? Okay. And just because of what we're going to do eventually, and what I know and hopefully can convey to you eventually, is that if I ask what the sine of 210 is, we will know that the sine of 210 will be negative 0.5. Okay, negative 0.5. The sine of 1290, we find out, is the same negative 0.5. Now, this is not a number that we have kind of memorized, sine of 1290. But we do have, eventually, the sine of 210 memorized. Okay? And I really don't have 210 memorized. I have sine of negative 30 memorized, which I say memorized. I don't know if it's memorization or if it's just knowledge. Okay, I'll never forget this because I've used it so much. It's just instinctual. We still get that negative. So I know that all of these things are the same. These two being coterminal. Now this one is not coterminal to that one, but knowing a relationship between negative 30 and 210 eventually will allow me to make the distinction that these two numbers are the same. But that's kind of where we're going with this, is that number is way too big for us to deal with. So can we dwindle it to an angle that is coterminal? So what I know about the angle of 210 degrees can tell me what I'm interested in for the angle of 1290 degrees. You've done this a little bit in geometry. This is finding the length of a circular arc. Now this has to be done in radians. It says in a circle of radius r, the length s of an arc that subtends a central angle of theta radians is s equals r theta. Okay, so let's just talk about the word subtends for a minute. If I've got my angle here, here's my initial ray, here's my terminating ray. Basically all it means is that, when it says subtends, is that there's an arc that is going to be defined or cut off and created by these two rays. Okay, so when I say subtended arc, we're talking about that arc that is between those two rays. If you remember back to geometry, basically what we said in geometry, we had a formula that if I wanted to find, so let's say we have this circle here, and I want to find the length of, let's say I just want to find the length of that red arc right there. Okay, what we did then was we said, well, this central angle right here, that central angle, in this case it's 90 degrees, that's the same measurement as the subtended arc out here. So if I want to find that length, then that length, okay, this 90 degrees, it's what portion of the circle. So 90 degrees compared to 360 is 1/4. So we would see that would be 1/4 the entire circle. And then I would multiply that by the circumference of the circle. So we had the formula in geometry where we call, I think in geometry we probably call that 90x degrees over 360 degrees. And our circumference was 2 pi r. So we had that formula. That's how we find the length, called it arc length, because we knew nothing of radians. Okay, that is this formula here. However, this was in degrees. Okay, if we do the same thing up here, but do it in radians, we get something that's a lot more convenient. Okay, so if I look at the situation here, that arc length right there, sorry about that, I had to find a charger. So if we're doing this in radians, okay, we can do something like this where we talked earlier that 90 degrees in radians was pi over 2 radians. And 360 is 2 pi. So if I do, like, let's say pi over 2 radians divided by 2 pi radians, so the radians cancel, and then multiply that by the circumference 2 pi r, what we're going to find out is, when I multiply this stuff out, so I'll have pi over 2 times now this. I'm going to have to do the reciprocal, so 2 pi. So the pi's cancel. I get 1/4 times then 2 pi r, and we get 1/4 of 2 is what, a half? So we get 1/2 pi r in that situation. Okay, and that's just a specific scenario. Like over here, I would get 90 being 90 times 360, or sorry, 90 divided by 360, that would be my 1/4, and then again times 2 pi r. Well, there you go again, 1/4 times 2 pi r, 1/4 times 2 pi r. So it shows you that they're equivalent. What happens, where this formula comes from, let's use kind of a general situation. Let's say we have this arc that is being subtended. I don't know how big this arc is, so let's say it's that arc right there. I don't know how big it is, so I'm just call it theta. Okay. Now, if I'm in radians, that theta is some proportion of the entire circle, which in radians, that entire circle is 2 pi. Well, then if I multiply that by 2 pi r, we can see right away that the 2 pi's cancel, and it just leaves you theta times r. So then arc length, which we denote with a lowercase s, is the same thing as r times theta, as long as theta is in radians. And there is maybe the first situation that we find out where and why it's more beneficial to work with radians than it is to work with degrees. In radians, arc length, very simple formula. In degrees, arc length, let's write it this way, a little bit more complex formula. There's no real nice simplification that occurs here if we're doing our work in degrees. But in radians, it's real nice. So the next question says, find the length of an arc of a circle with a radius 10 that subtends a central angle of 30 degrees. So we'd be looking at a 30-degree angle, and the arc right there is the length that we're looking for. So that S right there is what we're looking for. It says here R is 10. Okay. Now you can be a person that says, yeah, I'm going to do this formula right there because the problem was in degrees, so I'm going to do it in degrees. I'm going to use the formula that is provided in the box. Okay, but remember, theta has to be radians. Okay, now I know we don't have the greatest practice at this, but we did previously in one of the examples that 30 degrees was the same thing as pi over 6 radians. So if I've got my radius of 10 and I've got my pi over 6 radians, okay, and this was 10 meters, we end up with 10 pi over 6 meters. Okay, radians are, and I'll have a better description eventually about this, but radians are a dimensionless unit. And I'll work through the kind of the derivation of why we consider it dimensionless in maybe the next couple videos. So when it's compacted with or compounded maybe with another dimension or unit, meters another dimensional unit length, radians kind of just disappear. So we knew we were looking for arc length, so it's meters. Radian meters or median meter radians doesn't make sense for us. And like I said, I'll explain that in another video. Here it says a central angle theta in a circle of radius 4 meters is subtended by an arc of length s, or length 6 meters. Find the measure of theta in radians. So in this situation, just kind of draw the picture. It says central angle theta in a circle of radius 4 meters is subtended by an arc with a length of 6 meters. Find theta. Now, I don't know whether theta is going to be in the first, second, third, fourth quadrant here. I'm just drawing a picture to help me realize what I have and what I need. So I'm going to say that this is my subtended arc here, and it has a length of 6 meters. Okay. It says my radius is 4 meters, and I'm trying to figure out what theta is in radians. So we know that S your arc length is equal to r times theta. So S, which in this case is the 6 meters, is equal to r, which is your radius, so 4 times theta. So divide both sides by 4. I get 6/4 equals theta, so I get 3/2 is equal to theta. Okay, and what this tells me is that I have this in the right spot. Now, when we have something in radians, this is 3/2 radians. Okay, the pi doesn't have to be there. The pi is already kind of multiplied in here. Okay, we have, so 3/2 is 1.5. If you took your calculator and divided pi divided by 2, I believe that gives you about 1.57. Okay, so this is telling me, pi over 2 or 90 degrees would be 1.57 radians. So when they say 1.5 radians, our picture is probably more kind of like that. That would be the angle, and that would be the arc that we're talking about here. Area of a sector is really the same type of thing. I'm not going to derive the formula here for you, but it has to do with the fact that, again, maybe we'll take area for a circle. Dealing with a circle, we're going to go theta over 2 pi. So remember, a sector from geometry is just a slice of kind of the pie or the circle, the pizza, whatever you want to call it. So that's a sector. Okay, and we're trying to find that area. Well, that is a portion or some percentage of our entire circle. So, and that angle, that central angle there, theta, okay, whatever that angle there is going to be the same as that arc as a degree. So theta divided by 2 pi will tell me what proportion this angle is of the entire circle. And if I multiply by the area formula, which is pi r squared, you see that the pi's cancel. You're left with theta up top, 2 on the bottom, r squared. They factor out a 1/2, and they're left with theta r squared, and they just do some reorganizing of those variables. But that's kind of the derivation of that formula. But here it says find the area of a sector of a circle with a central angle of 60 degrees. Again, I don't like 60 degrees because these formulas are defined for radians. So 60 degrees, we convert that over to pi over 3 radians. So then if I want the area, it's going to be 1/2 r squared. So r is not, or r is 3, so r squared would be 9. And then we'll multiply that by pi over 3. And here is a situation where you see dealing with radians is going to be more convenient than degrees, because that 3 and that 9 cancel. I'm left with 1 times 3 times pi, which is 3 pi. And across the bottom, I'm left with just 2. And its area, we're dealing with meters. This would have been meters squared if I would have been following through with my units correctly. I think I'm going to stop there for today. Tomorrow we'll pick up with circular motion, and we'll get into that. Those seem to be we're going to see a lot of story problems in this course. I think circular motion are the ones that throw people off the most. So we'll get those out of the way. Hopefully make it seem a little bit easier than maybe you've seen some of this in physics. Hopefully I'll try to clean up any confusion that we might have from there.